All right, guys, we have the steps for partial fraction. We have the cases for how to create the partial fractions decompositions, and we have done a case 1 example. So now let's do a case 2 example. So this is going to be case 2. First thing I notice about this is that it is a rational function, and the degree of the numerator is 4, and the degree of the denominator is 3. Which means that I will need to start off by dividing here. So my step 1 of partial fractions is to divide if necessary. And in this case, it is necessary. So I'm going to have x cubed minus x squared minus x plus 1 goes into x to the 4th minus 2x squared plus 4x plus 1. X to the 4th over x cubed, that gives me an x that I multiply down. Notice I have this x cubed here, so if I want, I can be like plus 0x cubed so that things line up nicely. And then minus 2x squared plus 4x plus 1. Not necessary, but can be helpful. So x cubed minus x squared plus x that I am then subtracting. So x to the 4th minus x to the 4th, that's 0. Plus x cubed I end up with here, negative 2x squared. Oops, sorry about that, guys. Negative 2x squared plus x squared is positive x squared. So here I end up with a negative x squared, negative 2x squared plus x squared, then 4x minus x, that's plus 3x, and then plus 1. X cubed had disappeared. Okay, so we have x cubed minus x squared plus 3x plus 1. And now I want to keep going because the degree is still not less. So now I'm going to do plus 1, and I have x cubed minus x squared minus x plus 1 that I'm subtracting. And I get negative x squared, x cubed minus x cubed. So 3x plus x, that gives me a 4x. And then 1 minus 1, that's 0. So here I stop. This is my remainder. My degree is now less than the original denominator. So I end up with that this is equal to x plus 1 plus 4x over x cubed minus x squared minus x plus 1 dx. And notice that the resulting integral is not a known form. It's not a known form, and substitution doesn't work. The derivative of x cubed minus x squared minus x plus 1 is not 4x, which tells us, okay, still rational function, perhaps partial fractions is a good idea. So we're going to do partial fractions on just this part, this x plus 1. It will come back later. So our second step of partial fractions then is to factor the denominator. So here I have x cubed minus x squared minus x plus 1. So remember, to factor something like this, when we have a cubic polynomial like that, factoring by grouping is going to be the best way to go about it. So I'm going to group these into 2 little sections and find the greatest common factor of both of them. So over here, it's going to be x squared. And over here, I'm just going to factor out a negative 1. So in other words, I'll end up with x squared times x minus 1 minus 1 times x minus 1. And now notice that x minus 1 shows up on both sides. So I can have x minus 1 times x squared minus 1. But that x squared minus 1 can still be factored a little more. So this is x minus 1 times x minus 1 times x plus 1. And in partial fractions, it's going to be super important. If you have a factor that occurs more than one time, you need to combine it. So in other words, this is x minus 1 squared times x plus 1. So it's going to be super, super, super important to do that. Okay, so this brings me to my third step here. And my third step is to create my partial fractions decomposition. So I have 4x over x minus 1 squared times x plus 1. The fact that that x minus 1 occurs 2 times tells me that this is a case 2 problem, but these are all linear, which means that the numerators will still just be constants. So case 2 just means that x minus 1 squared gets 2 fractions of its own, the power increasing each time. So then I'll have plus x plus 1, and I'm just going to use ABC here for simplicity. So this is my partial fractions decomposition. Now, for step 4 of partial fractions, we start off by multiplying both sides by the original denominator. And in case 2 and case 4, actually, it's going to be super, super important that you do that and that you don't just like multiply by the denominators of the other letters on top. So in other words, I'm doing x minus 1 squared times x plus 1 each time. So what that means here is that I will have 4x, and a is not multiplied by x minus 1 squared times x plus 1. One of those x minus 1s cancels out. So x minus 1 time times x plus 1. Forgot to write a. So this is 4x is equal to a times that plus b, the x minus 1 squared cancels out, and I just have x plus 1 left. And then c, the x plus 1s cancel out, so I have x minus 1 squared left. Now, we're going to do method 1 again. Method 2, I find personally, we'll see it later, but it's usually only useful for cases 3 and 4 when you have quadratic factors on the bottom. So for method 1, now I'm picking the zeros of my denominator. So my zeros of my denominator are 1 and -1. So these are the values I'm going to start plugging in. So here I'll have x is equal to 1 that I plug into my equation. So I get 4 times 1 is equal to a times 0 plus b times 2 plus c times 0. And this gives me that 4 is equal to 2b. So b is equal to 2. And now I'm going to plug in the second 0. So that's x is equal to -1. So here I'll have 4 times -1. Again, my a cancels out. That's going to be multiplied by 0. This time my b also cancels out, and I'll have c times -2 squared. So I get -4 is equal to 4c, and c is equal to -1. Now the problem is we're out of zeros, but we still haven't solved for a. So if you're doing method 1 and you run out of zeros and you still have something left to solve for, we said that you should plug in x values starting with the zeros. Now I am going to plug in whatever x value I want, knowing that b is 2 and c is -1. So in other words, now I have 4x is equal to a times x minus 1 times x plus 1 plus b, which is 2 times x plus 1 plus c, which is -1 times x minus 1 squared. I'm going to plug in whatever x I want to solve for my last constant. Now plug in the x value of your choice. So that x value could be 2,764, it could be -91, but there are of course intelligent x values. I have not yet plugged in 0, so that's going to be a really good plan. So I will plug in 0, but again, I stress that's just because it's easy to plug in. And if you've already plugged in 0, so I'm plugging in the x value of your choice that has not already been plugged in. So if you've already plugged in 0, 1 might be good. In this case, I've already plugged in 1, so clearly that's not going to work. So pick an intelligent value. Pick a value that's going to be easy to plug in to the thing that you have. So I'm plugging in 0, and I'm going to get 0 is equal to a times -1 times +1 plus 2 times 1 minus 1 times -1 squared. So in other words, 0 is equal to -a plus 2 minus 1, and I get that a is equal to 1. So now I have my a, b, and c values. I'm on to step 5, which tells me to rewrite the integral. In this case, don't forget that we started off by dividing. So we had that x plus 1 out front. So I need to remember to write that when I'm rewriting the integral. It is somehow easy to forget. So here I will have the integral of x plus 1 plus a, which is 1, and my a was over x minus 1, plus b, which is 2, and my b was over x minus 1 squared. And then c, which is negative 1, and that was over x plus 1 dx. So all of these are known forms. This one we do want to be careful about because this is the same thing as 2 times x minus 1 to the negative 2. So this is not my ln known form. This is my ax plus b to the power of n known form. So when I write out my answer, I'm going to have 1/2 x squared plus x plus, this is a simple ln of the absolute value of x minus 1. Now this is going to be plus 2 x minus 1 to the negative 1. So then I multiply my negative 1 out front. And then minus ln of the absolute value of x plus 1 plus c. I'm going to simplify this, but this is my final answer. So 1/2 x squared plus x ln of x minus 1. This will be minus 2 over x minus 1 minus ln of x plus 1 plus a constant. Final answer. And we have just done a case 2 partial fractions problem.